So now we come to the greenhouse effect. Greenhouse effect comes from greenhouse gas. So what's the greenhouse gas? We see a greenhouse, right? It's greenhouse. Okay, sheltered glass. Now the air inside the greenhouse, greenhouse is warmer than than in the inside than outside, because the glass allows the solar radiation at the enter but prevent the outgoing longer wavelength radiation. Okay, so it also precludes the movement of the heat away from the surface by convection. So you see, I absorb all the heat, right? But we radiate, but then it can radiate some, but then the air gets heated up and heat conducts. So conduction, convection, radiations here, but due to this restraint this room here, convection cannot take place. You just get controlled in this house. So because of this, inside is a bit warmer than usual, and this effect, convection, right, makes the action of this greenhouse a bit different from the whole atmosphere. Okay, think of the local and the global level. Now for now, let's just refer to this as a atmospheric effect. Okay, greenhouse effect, atmospheric effect, because greenhouse effect is more well known. Okay, because of this term, people speak about it. But bear in mind that this analogy of the greenhouse is, describing, is a bit misleading sometimes. Okay, because greenhouse effect has a bit of a negative connotation. But what you want to say is it's just a very simple atmospheric effect. When you have a containment, radiation through glass, transparent come in, heat gets trapped because air cannot circulate upwards outside this localized region. Simple as that. Okay, so we prefer to call it atmospheric effect, neutral. Some greenhouse gases, common ones that we talk about in atmosphere topic: CO2, methane, right? N2O, nitrous oxide, hydrofluorocarbon, HFC 23 here, right? These are the from IPCC 2013. Now the global warming potential measures the potency of this greenhouse gas in warming the atmosphere with respect to CO2. So we take CO2 as a reference point, so as 1, okay, value. So here, across a 20-year horizon, right, a molecule of the methane is 84 times, okay, more potent, dangerous, okay, than a molecule of CO2 in terms of the global warming potential. Which means that if you have a choice, you have to release a gas, and we want to slow down the warming of the Earth, I will pick CO2 because it's a value of 1 compared to methane that's 84 times. I can save on 83 molecules of gases. And as you know, because a typical methane molecule, right, resides in the atmosphere for less time, shorter time, compared to typical CO2. So therefore, the methane's global warming potential is reduced, right, at a longer time horizon here. So you see, I want you to compare also the two columns here over 20-year period, 84:1. But over 100-year duration is less. The reason is because of what I just said. Because CH4, the molecular mass is 16, CO2 is 44, so it hangs around a bit longer. Look at N2O, okay, nitrous oxide, a laughing gas. 264, 265, marginally changed over what, 20 years, 100 years period. Look at the molecular mass. Look at the Earth's, our current climate's average MR, 79%, N2, 20% O2, etc. Okay, so note that although CO2 here is the least potent in terms of this global warming potential, right, this parameter we used to measure, it is the most abundant in the atmosphere. And also because of this greenhouse gas emission by human activity, normally when you burn fossil fuels, right, the exhaust from petroleum gas combustion here, we release CO2, right? So CO2 cause at least 2 times as much global warming effect than the Industrial Revolution combined from methane, your nitrous oxide, and the halocarbon combined. So here, what you want to understand is that those dosage is key as well. right? If you have the same dose, right, then methane gives you a more potent effect because it's more harmful, but you need to multiply by how much you have. You can have something that on low dosage level is harmless, but too much of it, CO2, yes, the overall potency, the effect is larger per se. Okay. Think of this question here. What if the Earth doesn't have greenhouse gas? What if all those gases we talked about in the previous slide, it doesn't exist? There's no greenhouse gas. Right? So recall, we assume that Earth is a black body. And a black body, that by definition is an object that absorbs all the incident electromagnetic energy regardless of its frequency. Just absorb. Black body absorb all the EM rays. Now, but this is a very highly simplified calculations, working on many assumptions, but it's imperfect. Now, things get more complicated when we take into account of the presence of the atmosphere and the effect on the temperature. And if you go back to this equation, the Stefan-Boltzmann equation here, and you make T temperature the subject, then you put the sigma the other side to a quarter power. This is the subject. So it relates to that if you do a simple substitution of the intensity, right, the constant, and this is the temperature, you found 254.6 Kelvin is less than 0 degrees Celsius. Okay. So think about this thought experiment. Okay. Now, why did the temperature here on the left graph, right, from the NASA Earth Observatory, why did the Earth's anomaly plateau in the late 1940, okay, to 1980 before increasing again? You see this little plateau here, and it spiked. It went up. Okay, it was pretty level. What about the years after 2000? Where are there any other plateau? Right, here's a little plateau. Don't mind this little peak here, okay? But it went down. It's pretty constant. Flat, right? Remember? 0 degrees, huh? But it spiked. So it turns out that the global temperature rose about 0.6 to 0.9 degrees Celsius between the year 1905 to 2005. Okay? It might look a very small number, not even 1 degree Celsius, right? But if you want to look back in the history, over the last 50 years, the speed of increment, temperature increment has nearly doubled. That is huge. We want to look at more examination of greenhouse gas emission here. So this is in the pole, the South Antarctica, perhaps near Chile, near the caps, the south. We study the dissolved gas components of the ice. Scientists do travel there in ships and boats here, and recently there's some bad news. You can read up on that about, people, there's too many males. There should be some diversity. But I digress. Scientists travel there to measure the historic level of atmospheric gas by drilling. Drill down, obtain some column of ice. Okay, ice. So ice is H2O, but there's dissolved gas, right? N2, a little bit. O2 can dissolve in water, which forms ice. Even your hydrates, methane hydrates, CH4 get trapped there. This is how some countries extract the natural resources, fuel, methane, okay, can dissolve. Methane ice, heard before? So this dissolved gas can provide data on the Earth's atmosphere as far back as 800,000 years ago. How do we do that? You know, as chemists, carbon dating. Carbon has a few isotopes, 12, 13, 14 here. And different era in our mankind, the proportion of this carbon level are different. At times there's a bit more carbon 12 than carbon 13 than carbon 14. Maybe the specific percentage changes over the years or in terms of time frame. So when we measure the carbon inside this ice at a certain depth, right, we can see, oh, at that point of time, right, which year was it? Then we can measure which year was it formed, and using the time and correlation, we can tell certain stories, okay? And compared to today, because today's carbon distribution level is different from 100,000 years ago. Okay, so we call this proxy indicators. You see the drill here? Put in and circle, and I have a little video similar but this for soil. Okay, check it out.